Good afternoon. So we will continue our discussion about convolutional neural networks today. And then in the latter part, we can discuss about object detection. That is the plan for today. So we discussed about one of the very first deep neural networks called AlexNet. And there we understood that they started with 227 by 227 images. And then they had convolutions, max pooling, convolutions, max pooling, several convolution layers, and then they flattened that, and then they had the fully connected layers, and then 1,000 node softmax, because ImageNet has 1,000 classes. Then we analyzed this AlexNet for the output size, the memory required for each of the layers, the trainable parameter count in each of the layers, and the computational load in megaflops. So then we realized, after analyzing all these things, that most of the memory is used in the early convolution layers. The reason is the tensor is of large size, because 227 by 227 is slowly reduced. Then secondly, nearly all parameters are in the fully connected layers, because convolutional neural networks do not have large parameters counts, and these have the parameter counts. And then finally, most of the floating point operations occur in the convolution layers. Then the next year, the winner was the so-called Seiler-Fergus network. They also had a similar structure, but this is the more important one, called VGGNet. So when they designed the AlexNet, there were so many things that these researchers designed by hand. But VGGNet gave some kind of a structure to the thinking that we need to have when we build a convolutional neural network. So you can see the AlexNet listed here. So AlexNet had the input image, then 11 by 11 convolutions, a pool, 5 by 5 convolutions pool, then three by 3 convolutions pool, and the three fully connected layers comprising of the 8-layer AlexNet. So what VGG said was, okay, we will not have convolutions other than 3 by 3 convolutions. Of course, when you say 3 by 3 convolutions, remember that the convolution kernel spans the number of input channels. So all convolutions are 3 by 3 convolutions. Can you see the rules of thumb they came up with? All convolutions are 3 by 3. All max poolings are 2 by 2 max poolings with stride 2. After pool, double the number of channels. So what that means is, when you have 228 here, after the pooling, the number of channels become 256, doubling the number of channels. So you can see this is now a sort of a clean structure that we can think about and reuse. That's the main contribution made by VGGNet. So you can see, if you take the AlexNet, there were 5 convolution layers. In the VGGNet, there are 5 convolutional stages. So you can see these are the stages 1, 2, 3, 4, 5 convolution stages. So VGG has much more parameters and consumes much more memory and floating point operations though. Then they had the 2 versions like VGG 16 and VGG 19. The difference you can see is having one more convolution layer in the 3rd stage and another one more convolution layer in the 4th stage and the 5th stage. So you can see that's what they show here. Within brackets, they show this convolution layer. So if you like, we can code this, but I will not start coding that, and it will take time for us to train this. But it is very much possible from the knowledge that you got from our coding of the Linux file. This kind of thing can be coded. I think half an hour, you'll be able to do that. So if you briefly study about these 3 by 3 convolutions, you can see there is a, I will not do the computations here, but I will only show you the numbers in the table. Number of parameters is 25 c squared. Here, number of parameters is 18 c squared. So you can see if you use 3 by 3 convolution layers instead of one 5 by 5 convolution, there is a gain in the reducing number of parameters. And the number of floating point operations, therefore, is also reduced. So this is a great advantage. But one thing is this 5 by 3 by 3 by 3 convolutions have the same receptive field as one 5 by 5 convolutions. We saw that when we studied about the receptive field last time. Receptive field means if you take in this layer, if you take one element, it received input from these 3 by 3 elements. And if you take this element, that received input from this 3 by 3. And if you take this element, that received input from this 3 by 3. So you can see the receptive field is 5 by 5, right? So the same effect of the 5 by 5 convolution is there if you use 2 by 2, 3 by 3 convolutions, but there are advantages in the computation and the floating point parameters. That's why these 3 by 3 convolutions are advantages. And then there are other things also, but we will not talk about those things, the doubling the number of channels and all these things. Yeah. In 2014, Google Net came. They had some interesting things. They used STEM network to drastically reduce the number of uh, the size of the tensor, so that the storage and the computations become less because of that. So then they had this thing called inception module, where they mix 3 by 3 convolutions, 5 by 5 convolutions, and 1 by 1 convolutions, and the so-called global average pooling. They take the output tensor structure and spatially they average it out. That's called global average pooling. But I will not analyze this network for you. So this is the so-called inception module, where they had 3 by 3 convolutions, 5 by 5, and so on. And then we can see this global average pooling, that we will pay a little bit attention to that. Now you can see in this case the height and width of 7, that means 7 by 7. So kernel size is 7 by 7. Side is of course 1, and there is no padding. So if you run a 7 by 7 kernel here, so you can see the kernel fully spatially overlaps with the output structure size, right? The output structure or the output tensor is 7 by 7, and the depth of that structure, number of channels, is 1024. So exactly the same size of 7 by 7 stride 1, and because of this reason, you will by input number of channels is 1024. Yeah, not too sure about that. So anyways, the spatial size became 1 by 1 in this case. So you can see, I'm sorry, it's not a convolution, global average pooling. What that means is you take one slice here and then get the average of that and put it there. So after that, you have to map it to 1,000 numbers. That's what confused me, 1,000 numbers, because there are 1,000 classes. Yeah, that is something else. So that's what global average pooling means. Yeah, this only shows the global average pooling. Yes, global means spatially global. Okay, so then it had some auxiliary classifiers also. Why? Because the backpropagation did not happen here, because this network is too deep. So because backpropagation did not happen, they had to have auxiliary classifiers to feed the feed the lost signal to run it backwards. Because by this time, the so-called batch normalization had not been discovered. So when you do this so-called batch normalization, do some normalization, gradients start to propagate. By this time, it was not known, so that's why this was there. So if you summarize the things that we studied under this section, ImageNet large-scale visual recognition challenge was there, which is called ILSVRC, and AlexNet was introduced, that revolutionized everything. It introduced max pooling, relieved nonlinearity, large number of parameters. And then VGG, they said all convolutions must be 3 by 3 stride 1 pad 1. All max pools are 2 by 2 stride 2. After pooling, double the number of channels. GoogleNet introduced the STEM network, inception module, and the global average pooling, which is something people use even now. Okay. Now in 2015, there was an important network that was introduced called the residual network. Before going into details of that, let me ask whether you have any questions. Please don't hesitate to ask. I know only two are there, but I very much appreciate you joining this. Lanka and Mr. Malapat are there. So if you have any question, please ask.
So when we are dealing with very large pictures, we might need to first break these pictures into smaller pictures and then do the this processing. Is the approach different in that case?
It is very true, very true. Usually what they do is they will resize it to 224 by 224 to feed to these networks. Or like you said, you can break into small images also. But usually, since we want to make a decision for each image, right, whether this image is a dog image or cat image, right? Because image-based decisions are required in classification, we usually scale it to 224 by 224. That's a
Okay,
very
sir.
important question actually.
So the second thing is by 2015, did we have this GPU, was GPU used in processing or was it
Yeah,
not?
because why is that's a important thing to know because AlexNet, if you remember, they use a GPU, right? They use GPUs, but they did not have this TensorFlow or the PyTorch. So what they had to do is they had to manually write these things in CUDA. See, the GPUs are there. They ran it on two 3 GB GPUs. That's one of the main advancements of that AlexNet.
Okay, sir. Thank you.
Yeah, it's a very important observation, actually. So they work very hard to do that.
So one more thing in that, this slide. Now now I can see some towers. Maybe I missed the previous lectures, but can you tell me the difference between the three colors, the blue, orange, and red color? What's the
Yes,
difference?
yes. Now these convolutions run the so-called convolution operation, right? So what is the convolution operation? Now if you take an input image or an input tensor like this, and now you keep this convolution kernel on top of that. You keep a 3 by 3 kernel on the input structure. So this side is 3, this side is 3, and maybe this depth, let's say 64. Although I call it an image, it can be any a tensor at a latter part of the network also. So this 3 by 3 times 64 set of numbers, weights. So 3 by 3, 64 times 3 by 3. So all the underlying image pixels or the values in the tensor are multiplied by the values in this blue kernel. That's the how compute one element of the output structure. And then you move it spatially, this 3 by 3 thing. So this is one convolution kernel running throughout the image. So that's what you show by the yellow layers. And the pooling layers, they just make the size usually half. In the pooling, if you have
Is it some kind of compression, sir?
Some kind of compression, but it is a very simple thing than regular compression when you think about it. So what they will do is they will if this one is size 224 by 224. Okay, I'm taking some stupid size, I think 24. If you run 2 by 2 max pooling, the size will become okay. Number of channels, let's say 64 or something. I think I should not select this site. So it gives the wrong idea. let's say that this size is 50 by 50 or something. 50. So if you run max pooling, this 64 will remain, okay? Number of channels, this size will become 25 by 25. 25 by 25.
Can we say it's a change in dimensions without losing too much data
Data
or
is lost.
information?
Information is lost. Information is lost. Because we pick the maximum value. That's what max pooling means. So information is definitely lost. But it is okay. So if you remember this max pooling thing, remember this max pooling? Can you see that? You take a slice of the image. Max pooling means now out of these four numbers, you pick the maximum. It's 6. Out of these four numbers, you pick the maximum. That is 8. Out of these four numbers, and so on, right? So now the input structure was 4 by 4. It's a toy example. But the output size became 2 by 2. It becomes half. If you use the so-called stride 2, that means you move by 2 pixels at a time. So
Okay,
that's what
sir.
max pooling is. So
It's
the
a kind of
purpose
it's a kind of compression then. I mean,
kind
looks
of
like it.
compression, and you lose information. Why
Okay.
do we do that? Now, because of this reduction of the size, although you reduce the size, you can see this 6 sort of has information of all these things. Sort of has. When you take in a convolution neural network, in the latter part, if you take one element, just one element, that element would have given rise from a large number of pixels in the input, maybe 50 by 50 range, 50 by 50. So whatever the objects that have been there here would have influenced this one. So you can make a decision on those objects using that one single number. That's why you keep on reducing the spatial size in a network.
Like a statistical significance.
Yes, yes, yes. So people have understood that this is important to do object classification or the represent image classification to represent images.
So the second thing is like if you compare the tower diagram to the one in a straight line, I can't really understand how they map to each other.
This tower is a representative diagram, but when you say 3 by 3 con 128, so you have to show that using a big box.
So there was another diagram, a straight line diagram or like a flow diagram with some different, like a branching tree. I
You
think
mean
it
the
was before the
Google
color with the colors, yeah, similar colors. I think,
this one?
yeah, this one.
This one is a Google net. So that also has these kind of layers. But in the so-called inception module, they have a combination of convolutions. 3 by 3, 5 by 5, and so on. So the same input is fed to this, fed to that, fed to that, fed to that, and so on. Because they thought this combination is important.
Okay,
Different
slightly
sizes of
different architecture.
So yeah, very different architecture. They thought that this having a 3 by 3 input, 5 by 5 input, and so on is important. But they are wrong. They don't. You don't really need that. That's a misconception. So
Okay,
you
sir.
see, like people make mistakes in their life. For very famous people, okay. So people slowly understand as a community, right, what to be done. Yeah, now we know it is not a useful thing, but then people did not think like that. Yeah. Any other questions? Thank you for those questions. These are very important. Okay, then let's understand this the concept of ResNet. This is one of the most important contributions. Mm. So, with so-called batch normalization, deeper models could be trained. Now, the networks are not 8 layers like AlecNet or 16 or 19 by VGGNet. Now, the networks can be deep. Deeper models, but unfortunately, deeper model does worse than the shallow model. People realized that. So they thought bigger is not better in contrast to previous experience. Initial guess was overfitting because now this is the number of iterations, how many times that you run the images through the network, and this is the test error. Test error. So the test error for the 20-layer network is less compared to the much larger, much deeper 56-layer network. So this they observed. So this kind of thing happened if you overfit. Overfit means the network remembers the training images so much that when you give a test image, it is doing not so good. So people thought that's a problem. This kind of thing is called overfitting. But when they observed the training error, so in training error, the larger network must do better because there are so many parameters to memorize the images. But in the training error wise also, the larger network was doing worse. So therefore, they concluded that 56-layer network has not been able to properly learn in testing and in training. So there must be an optimization error here. So they proved that using by construction, in fact, deep models seem to be underfitting since it also performs worse than the shallow model on the training set. It is actually underfitting. 56-layer network has not been able to emulate the 20-layer network. So a deeper model can emulate shallow models. So therefore, they constructed a proof, copy the layers from the shallow model and set the extra layers to identity. They said, let's do that like that. So now, so let's take a network. It has 20 layers. So it is having some accuracy. Let's say 10% is the error rate or something. 10% error rate. Then what you do is you take this network and you connect additional 36 layers. Each of the 36 layers, they don't do anything, they just multiply by 1. There's 20 layers, and these 36 layers, they just multiply by 1. So, now if this is the case, the error should be 10% because he did not do anything. So, but it did not turn out to be like that. That is the problem. So if you copy the layers from a shallow model to extra layers to identity means multiply by 1, the deeper model should do at least as good as a shallow model, but this did not happen. So hypothesis, this is an optimization problem. Deeper model are harder to optimize. And in particular, don't learn the identity function to emulate the shallow models. They cannot learn one. They cannot learn multiply by 1 function. That is the problem. So they identified that and they came up with a solution for that. Let's see what the solution is. Solution, change the network so learning identity function with extra layers is easy. So they took a block. What is that block? There's an input and there's a convolution. There's a ReLU, a nonlinearity, and another convolution and some output function. What they did was, now you want to learn the identity function. Identity means multiply by 1, right? They added a shortcut connection. So this is exactly when you add a shortcut connection like that, it just feeds x to the output, right? So if you forget about this and that, it is just multiplying by 1. So can you see the genius solution? So this is called an additive shortcut, makes the gradient flow also efficient. So as you saw, like when you feed the gradient backwards, you have to go through these computational nodes. Now it is not going through a computational node, so gradient is properly fed back. So if your network, the function that is applied by these two layers is fx, now it is fx plus x. So these are called skip connections, and that is the great. So you can see it is a residual that this part captures the residual. So that's why they are called residual networks. So it's a beautiful concept. So these are set to 0. If these are set to 0, the block will compute the identity function. So with this residual connection, they were able to get very deep networks. A residual network is a stack of many residual blocks, regular design like VGG. Each block has 2 3x3 convolutions. Network is divided into stages. The first block of each stage halves the resolution, which is tied to conv and doubles the number of channels. So you can see, if you take this example, first of all, you can see the skip connections here. Can you see after 2 layers, there's a skip connection, right? That's cheap connection. This, if you take this one stage like that, number of channels is 64, and uh, halves the number of channels. So halves the resolution and doubles the number of channels. You can see the number of channels becomes 2, and the resolution becomes half. Yeah, so this is what the ResNet was. And of course, this global average pooling and fully connected to 1000 is there because there are 1000 classes. Yeah, use the same aggressive stem of the GoogleNet to downsample the input by 4 times before applying residual blocks. Then, like GoogleNet, no big fully connected layers. Instead, use global average pooling and a single linear layer at the end. So because of that contribution, they were able to come up with so many networks called ResNet 18, ResNet 34, and so on. If you briefly, all these things can be downloaded and run by you. If you take ResNet, one convolution layer, so stage one, 64 channels, two residual blocks. So therefore, altogether, 2 times 2, 4 convolution layers. Stage two, two residual blocks, and each block has two convolution layers. So therefore, 4 convolution layers, and so on. So 4, 4, 4, 4, and then the linear layer here, and then altogether plus this 18 layers. So they had ResNet 34 and so on. So
So
one more
if you
yes.
want to if you want to assess the knowledge of the people who are developing this, is it more is it in terms of percentages? Is it mathematics, software development, algorithmic development, or some other thing in terms of ratios?
Are you asking about the how they design these kind of networks to get a publication?
What kind of knowledge they require to do this kind of work? What is the core, like, is it mathematics or is it algorithmic knowledge or is it statistics or software
Mm,
development?
I think it is a combination. You are experienced it with the most of these things, and then you think about the problem, why that happens. So, software knowledge, your mathematics knowledge, your statistics knowledge, and your knowledge about the running a computation, all these things are just tools. Then you think about why this error is happening, and then you come up with an idea. So it is a very big challenge actually coming up with a research idea.
Okay,
So
sir.
they have to be equipped with all the knowledge components actually. These are
Is
very
it
smart people actually.
is it a team of people doing this work or is it one or two people?
3 or 4 people usually. This each paper is authored by 3 or 4 people, right? So the
Okay.
idea comes from one person usually. The idea usually comes from the student. Maybe Kai Ming he has, in this case, he's the first author of this paper. And also, there is a very famous paper called Mask Autoencoders, MAE paper. There also, he's the first author. So this person, he has the capacity to generate these revolutionary ideas, simple but revolutionary ideas.
So what's the name again?
Kai Ming He.
Oh,
You can see I have written the paper's name here, but maybe you cannot see that. I'll show a picture of this person. So he worked for Microsoft at that time. This person, he worked for Microsoft. Now you can see this is ResNet pair, deep residual learning lane. So this is cited by 325,000 times. I think this must be the highest cited paper of all time.
his
Past art opinion.
his
Yeah, there are also.
BSc his BSc was electrical engineering, sir, or mathematics or some computer science?
I don't know. It's computer scientist. Xinhua. What did he do? And in MIT, computer scientist, they say.
Okay, sir.
We don't know what he did in undergrads.
No, it's okay, sir. I'll look at it later. Thank you, sir, for sharing.
Yeah. Uh, Bachelor of Science degree in 2007.
Information engineering. Oh, that's later.
Uh,
Also, doctorate studies in information engineering. Oh, that's later, sir.
yeah. He's a very, I mean, many contributions to the research world is by this person. And so they had other things also. So they had so-called this residual block, okay, that we studied. And then he said, okay, this residual block also has a little bit of problem, too much computation. And then he came up with a mechanism to reduce the number of computations in the same paper. And so that reduced, so this computation is not very meaningful. Actually, it reduces much more than that. So this is called a bottleneck residual block. So with this, there is some calculation also. You can see when you use the bottleneck residual block, I will not calculate and show. You can reduce the number of computations from 600,000 to 70,000. So you can see how good these people are, right, to come up with these ideas. So then with that, they were able to come up with ResNet 50 and so on. There are 50 layers, ResNet 50, ResNet 101, ResNet 152, and so on. They were able to come up with. So you can see here they use bottleneck layers. They use bottleneck layers with ResNet 50 onwards. Okay, let me see whether we can get a quick network running and working on one of our data sets with ResNet. We can download the ResNet and see whether I can code that quickly so that you can see how to use an existing ResNet and um, work with it. So let me see whether I have that code written. So parts of it I will code, parts of it I will just show you. Okay. Um, so I need some uh, some images. Okay, so I will create that folder here. So there's a data folder here. Let me show you how I do that. So please watch this. It's an important example that we are doing now. I'll give you most of the code. So see, I'm working on this folder. And I have the code folder, so I have a data folder. So to that, I'm going to copy some images. So these are called persons. Okay, so persons images I'm copying. Huh? Okay, now I will send you that persons images if you also want to do that by chat. Yeah. Okay, so I'll send you that one. So if you look at this, you will look at this carefully. So I have four persons. Keira Knightley. I have 10 images of her. And then I have 10 images of Ryan Reynolds, and I have 10 images of Scarlett Johansson. What happened here? What is this? So maybe I had to get them downloaded, otherwise it won't work. So I have to click each of them. Okay, all the images are now on my drive. Then finally, I have another folder. This is the most important folder. It's the folder of Ranjan Ramanayake. Yeah. Different sizes of images. There are different sizes. You can see already some of them are large, some of them are small. So as you asked, we have to resize them to a certain size. That is to the size the network expects, the 224 by 224 in this case. Yeah, different images. I worked very hard to get these images downloaded. He used to be Honorable Ranjan Ramanayaka. If you do not know him, that's very strange. If you do not know him, he's a famous movie star in Sri Lanka. He likes to call himself actually Hela Cinemave Ginisilu. Yeah, okay. Now you can see what is there. So this has, like you can see, 4 classes are there, and each class I have put 10 images. So okay, Ryan's images also, some are not here. Get all of them downloaded. So now you can see this is my problem, right? I want to classify between Ryan Reynolds, Carla Johansson, Keira Knightley, and of course Ranjan Ramanayaka. But I do not want to train a network from scratch, but I want to fine tune an existing network. So I will use ResNet and download the ImageNet weight. So ResNet has been trained by ImageNet by people. So I'm going to download that. So a few of these things I will code, and a few of these I will copy, because otherwise it will take a long time to type all these things. So first of all, I will do the imports, import copy or something, and import random for randomization, import random, then import from path because I want to access those folders. Import path. From pathlib import path. From pathlib import path, then yeah, okay. From pathlib import path, so capital path. It's done. So let's we import the other ones also. Of course, you know that we know PyTorch, import torch, and import torch neural networks, import torch.nn as nn neural networks, and then torch optim as optim, import torch.optim as optim, and then data utilities, import torch utils data as data loader, and I want to get the subset also. And then torch vision, I'm going to import the models. Torch vision, import datasets, transforms. I want dataset, transforms, and models. And then from torch vision models, include ResNet weights, ResNet 50 weights. From torch model, no, this torch model, import ResNet. Oh, I'm sorry. Torch vision. Torch vision models, import ResNet. ResNet 18 weights. Okay, you get the ResNet 18 weights. Okay. So I hope these are clear to you what we are doing. Is that clear what we are doing? ResNet 18 weights. Do you understand what that means? So these weights someone must have trained, and they are kept on this Someone means this PyTorch people have trained that they have kept those weights. Those are ImageNet weights. What that means is they have trained the network using ImageNet. We are going to use those weights and adapt to our work, which is called uh, transfer learning and fine tuning. We see the difference later. Now, it's first the configuration. Configuration I will type out. First of all, a data directory. Yeah, so it's in my data and it's in persons, right? Persons. Yeah, persons. So batch size, so it's batch size. I have small number of images, so I'll say batch size is 2 or something. Okay, then number of epochs. Uh, Maybe 8 epochs. Then I want the seed because why do I need the seed? If I don't have the seed, every time I run, I'll get a different output. So I'm not able to diagnose. That's why I have that. And okay, so number of epochs for the first of all the head epochs. Head that is only training the last layer. Then for the fine tune also, I'm going to write about fine tune epochs. You see, I'm going to do two things. For fine tuning, maybe let's should have a little bit of maybe 24 something, large number of epochs for that, because you are affecting the whole all the weights and the learning rates. Learning rate for the first one, and for that learning rate can be a little bit large, 1e minus 3. But for the fine tuning one, learning rate must be small because you don't want to uh, middle with the weights, existing weights. So I need the ImageNet mean and image. So this for ImageNet images mean. These means are well-known means and standard deviation for these ImageNet image ones. So we need those also. Okay, so some functions I will copy. Define the seed, set the seed, and so on. I will get that. That is okay. And then I will have the evaluate one to print the accuracy and so on. That also I will copy from my previous work. Let me run this and see whether I made a mistake. Yeah, that is to when to run one epoch. Also, I will copy that. So there you can see this is the training part, model train, and you take X and Y, these images, you cast them to the device, GPU or the CPU. We have already done these kind of works, and we zero the gradients of the optimizer, and then we compute the loss and say loss backward, right? And then step the optimizer. We have already done that last time. This is the typical back propagation pipeline. So then validating the image path, for that I have function. Um, so then so to generating the balanced data set. So there you can see from the image folder, I will get a random number generator. From that, I extract some of these images. This is for the for training and validation. I can extract the images from the directory that I have. Then we set the seed and device, and then if the directory is not there, complain. All these lines are these. So let's see whether this is running. Okay, device is queued up because I have a GPU card on my machine. I'm very happy about that. Then do the transformations, because when you get these images, remember they have to be changed to the size of uh, the uh, what the ResNet 18 can accept. ImageNet mean, why is it highlighting? Is it not correct? I wrote image net ImageNet mean that image net std. So okay, image net with the standard deviation, that's okay. All right, so you can see resize them to crop, take out by 2 size ones. Complaining ImageNet V2. So let me see whether ResNet 18 is there. ResNet 18, wait. Let's try without the V2. So let me ask the AI for this. Then it's easy for me. What's the error? What the error is? I don't know actually whether these dates are available. In the meantime, I will get others copied. So reading the data set from the folder structure and getting the train indices and test indices and the applying the transformations and these things. It's still running. Only has V1. That's a problem. Okay, it's done. So this part. So these are for, you can see, building the data set. So these are data set operations. So therefore, I will not spend too much time on that. Batch time, number of workers I did not put. Number of workers. Okay, that is okay. Then comes the important part. Okay, now you please watch. I will type line by line now. So now get model is our model setup. Okay, model setup is our model is ResNet 18 with pre-trained weights. Yeah. Replace final layer for 4 classes. 4 classes. Okay. Okay. So model. This is important. Equals models. This is from Torch Vision. ResNet 18 weights. So we have said what the weights are. ResNet 18 weights, ImageNet 1K P1 weight. Okay, so this is the model. And then we will have in features model fully connected in features. So for the fully connected layer, input features, and then model fully connected, we are putting a new layer. Now you see that we are putting a new linear layer with the in features what we extracted from here. Out features number of classes. Number of classes in our case will be 4. Number of classes length class name. So 4. So maybe you can print the class names. So you can see the class names are 1, 2, 3, 4, 4 classes, right? So this is you are removing the top layer from ResNet and putting a layer. Top layer in the ResNet will have 1000 outputs. Now I'm giving only 4 outputs because I have only 4 classes. So I hope that is clear. And model to device, we cast it to the GPU that I have. Then I need to define a criterion criterion cross entropy. Optimize for this. First, optimizer will do the optimizer later. Then validation loss before, accuracy before and after fine tuning. After we can have validation loss before, validation loss before, validation accuracy before, evaluate model to device, and then we can print that also. So this is without training. We can now run that and see what happens. So it's downloading the weights, ResNet 18 weights, it's downloading. So it has downloaded 44 and it should give me the accuracy. So you can see the validation accuracy is 25%. So 25% means random. I have 4 classes, right? So minimum that it can get is 25%. That is nothing is happening. I mean, it is not correct. So that's why we need to take that last layer and do something. So train the head only. Head only. So for that, we can parameters in model, parameters requires grad false. We don't want to run the gradient through the whole model, but we want to, for the parameters in the fully connected one, we say gradient true. Only the train, only the fully connected layer at the top. I hope you understand this. If you have a question, you have to ask at this stage, because this is a very important thing. You're only training the last layer we added. So now optimize ahead and so on, optimize ahead, Adam optimizer. It's a very good optimizer. And we have to put the model and actually the learning rate we have already defined, and then the best model weights. So these are model weights. So we copy the best weights and then best accuracy, 0 something, not 0 something, 0 print. So we are starting the training the head. Yeah, that's good enough. Training the head, and then epochs, head epochs. Then train lost training accuracy. So train for one epoch, that function we wrote, I copied, so that is okay. And validation loss, and you say evaluate, and we can print, and then based on the validation, if the validation accuracy is greater than the best accuracy, we change the best accuracy, validation accuracy, best model weights, we can deep copy that, and then we can do a print. It's annoying. Print. I'll copy the print part. Okay. So then model dot load state dictionary base model weights. Yeah. So we get the base model weights after this fine tuning, the transfer learning part that we did. So we can print the accuracies now again. Here we can do that. Validation loss after evaluate model. Criterion. There's no problem here. Criterion. Any mistake there? Okay. So it is running. So it will do 8 epochs. Run the dataset 8 times through the network, and then hopefully the validation accuracy should improve. 25% is random. There are 4 classes, 25% is random. If you have 10 classes, 10% is random.
So what's the reason of only training one layer?
Yeah, that's a very good question.
Efficiency?
Because we do not, yeah, because if you don't have too much computation, we only train the last one. So you can see that you train for that many epochs. So now validation accuracy has improved, right? 50%. Much better, right? 50%. Much better than 25%. So this is the epoch number 1. So it is training.
So when they train these large language models, do they use some approach like this? I mean, not exactly like this, but something similar to this.
Yeah. Because large language models, you have foundation models. They are large models trained by companies, right? And then we use them, and we will want to adapt them to our own work. So fine tuning is one method that we do. Actually, we are going to organize a talk about this fine tuning. We will probably do it in Colombo something to show how to fine tune large language models and vision language models.
Oh, okay, thank you.
So in this case, validation accuracy became 100. I think just training that is sufficient, I think. Yeah, training that was sufficient. Mm. So that is okay. Now we can fine tune the entire model. So
It
yeah,
can
now
be,
it has,
could it be overfitting, sir? Because this is the training validation, isn't it, sir?
it cannot be often because for the validation, training data is not used, right?
Yeah, okay.
Yeah. Anyway, because of the small number of examples, these things are erratic. Okay, you cannot fully explain these things with these 10, 40 images. Okay, so you should have had some more images. Okay, 50 or something like that. So okay, 74. So then the next part is we have to do the full fine tuning. That is called not transfer learning, fine tuning. Okay, so that we will do on pre-solve and avatars of fine tuning. So for this one, see that this is the most important one. Require get true for all the parameters of the model. Now require
So
get true
is
for all
this
the.
same thing as hyperparameter training or tuning, or is different?
Say it again. What?
Hyperparameter
No, no,
tuning?
no, 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 absolutely no. No, these are not hyperparameters. These are the actual parameters of the ResNet 18.
Ah,
All
okay,
the
sir.
convolution layers, all the fully connected, all are trained. So many parameters. If you like, we can calculate how many parameters are there in the ResNet that we can see. Okay, we will do some.
So what's the difference between the hyperparameter tuning and this tuning, this
Yeah,
model
okay.
tuning?
So now here, if you take the ResNet or something, the only hyperparameters are, for example, the learning rate. They are outside the network. They are not parameters inside the network. Mm. Uh,
Okay, like to do the training outside these are certain
Outside the network.
settings.
Yes,
Ah, okay.
yes. Those are the so-called hyperparameters. Learning rate. If you have a loss function, the alpha that you use in that loss function to balance the losses between this loss and that loss. Those are called hyperparameters outside the network. These are inside the network parameters. Yeah.
Okay. So can we say the hyperparameter tuning is like more generic kind of tuning rather than more model specific tuning?
Uh, yeah, for that specific module, we can find the best set of hyperparameters by hyperparameter tuning. Yes. For example, if you take k nearest neighbor, how many k's are required? That's a hyperparameter, right? What is the k that you want? So that's a hyperparameter.
Then how would you specify the parameters within the model? Or what
Within the
would
model, parameters have been specified when they define the ResNet 18. So we did not get the ResNet 18 definition, no? Because we downloaded ResNet 18, right? ResNet 18 model we downloaded, so we did not define it here. But if you remember, for the MNIST, we wrote, see, do you remember? Last time we wrote con1, convolution 2D, input number of channels is 1, output is 6, kernel size is 5. So how many parameters are here? Kernel size is 5, so 5 by 5 times 6, right? That is 150, and the biases are there, 156 parameters in that layer. Like that, we can compute. Here, input number of channels is 6, output number of channels is 16, kernel size is 5. So 6 times 5 times 5 times 16 parameters plus 16. That's the number of parameters in that. So for each different types of layers, like convolutions, how many parameters? For fully connected layer, how many parameters? We can compute that.
So what you're saying is for the ResNet, we can take the standard settings and change them to customize them, like what
Yes.
is here.
Yeah. Now, if we define these for the ResNet, these parameters have only randomly initialized. These 156 parameters here will be randomly initialized.
Oh, okay, randomly,
The,
not
the,
fixed.
okay, okay, these parameters will also be randomly initialized. But here you can see we are downloading the ImageNet 1000 weights, right? Can you see that?
Okay.
Now the parameters are not randomly initialized, but they are initialized by the ImageNet 1K parameters, already tuned, already tuned. So for this network, if you just give an image of a cat or something, it will recognize at once, because ImageNet has all these images. But it is not able to recognize Ranjan, Scarlet, and so on, because it has not been trained with those images. That's
Okay,
why
I think I got it. Okay.
we need to transfer
Retrain.
learn. That means train the last layer or fully fine tune. Yeah.
Oh,
Yeah. So I'm glad that you asked these questions. Otherwise, these are not. I also did not say them. Tell them. Yeah. So now the thing that we are doing is require parameters. We said require that true for all the layers. Initially, we said it's false, right? And we only unfroze the last layer. But now we are unfreezing all the layers. Then optimizer and so on, we will I will copy. It's the same thing from the previous part. Optimizer, Adam, and learning rate, fine-tune learning rate. Remember, the fine-tune learning rate is smaller than the learning rate that we should take for transfer learning. Then all the other things also I will copy, because they are sort of the same as before. And then save model is there, and then ImageNet. We can print the validation accuracy after fine tuning. Yeah, okay. So now we can run. So it will run again twice. It will run those 80% twice. So, so I can draw a few things and show you what we did here. So what we did was we took the so-called ResNet 18. So this is our ResNet 18. ResNet 18. So it has 18 layers, right? What is the last layer? Last layer is the softmax layer with 1000 outputs. There are 1000 nodes in that. Why? Because it has been trained with the ImageNet large scale visual recognition challenge. So this layer. So what you want to do is we want to take that thing off. We removed that. We removed that. And what we did was we took this part of the network and we connected our own output layer, and that output layer is different from the previous layer. Why? Because this should have only 4 nodes. Why 4 nodes? Because we have only 4 classes: Scarlett, Kera, Ryan, and Honorable Ranjan Ramanayaka. So then we have 2 choices to adapt this network. One choice is we can only train this part. That one we train with we call it transfer learning. We train with a higher learning rate. That's the phase 1. In the second phase, P2, what we did is we used the same weights and we affected the full network. Not only that, we let all the weights in this network be changed, unfroze all of them. This is called fine tuning. This is usually called transfer learning. I hope it is clear for you what we are doing here. Okay, so let's see what has happened here. So this is only the first training. The training the head is happening only. Training the head is transfer learning. This one is not still happening. The training the full model has not started because it takes time. You can see, right? Even for those 40 images, it is taking time. Although I have a GPU here, so that now you can see, like if you want to train with 1 million images of image, that is absolutely not possible with my machine. Take time. So that's why we have to use existing weights and do something. Okay. So until that trains, we can think about some other thing. So they have improved residual blocks and so on. So introducing batch normalizations here rather than they are and switching this. So we will not talk about them too much. So then people looked at all these models based on the top one accuracy and the number of operations that each model requires and the size of the model. So you can see in the right hand side graph here, you can see the number of operations that it needs, and it shows the size of the model also, and it shows the top one accuracy on the ImageNet. So you can see some large models have been there. VGG19 requires so much computation, and the model size is also very large, so their performance was this much. But then other networks came like ResNet 152 and so on. The ResNet 152, you can see the operations is less and the model size is reasonable and the accuracy is good. But then there are other things that came after ResNet which had high performance. So ResNet 18, you can see the performance, computations are less, performance is less. The reason is it's a smaller model. Yeah. So there have been many other models, but I will not talk about all these things. Anything else that you want to know about this? Yeah, so these models are there. So you can look at the slides. So there have been other winners, so-called. Then after that, the parallel pathways were introduced. These led to so-called depth-wise convolutions. They are very important because to make the network small in size and faster, they have to use these things. So then in 2017, they introduced squeeze and excitation networks. They are channel-wise weighting happened. So I will not go into a lot of details here, but you can see the squeeze and excitation networks. And then see connected neural networks in 2017. Then mobile nets for tiny networks for mobile devices again in 2017. And then neural architecture search. This concept is also very important here. Okay, this you can say hyperparameter tuning. They had number of filters, filter height, filter width, this convolution filter size, side height, side width. These parameters they were able to tune using another network. This child network was tuned using another network. So this is called NASO neural architecture search. So that came up with very powerful networks. So if I summarize all these things, early networks like AlexNet, Xylophagous network, BGGNet showed bigger networks work better. GoogleNet, one of the first to focus on efficiency, aggressive stem to downsample, one by one bottleneck and so on. Convolutions, okay, there's a mistake in this slide. Sorry about that. Bottleneck convolution, global average pooling, and instead of fully connected layers and so on. These were the things that were introduced by GoogleNet. Then ResNet showed how to train extremely deep networks limited only by the GPU memory, started to show diminishing returns as the network got bigger and bigger. After ResNet, efficient networks became central. How can we improve the accuracy without increasing the complexity? Lots of tiny networks aimed at mobile devices like MobileNet, ShuffleNet, and others. Neural architecture search promises to automate the architecture design. So then they came up with this efficient net. That's also a good contribution. When you double the amount of resources, how should you resize the network? So they designed a network called B node, and then you can see number of parameters and top one accuracy. It's much higher than the networks that we studied, like ResNet and ResNext and so on. So efficient nets are very good. So I will not give you a lot of details about the efficient net. Then in 2022, they came up with ConNext, that mimics the operation of the so-called transformers. These transformers in the new paradigm, they were able to, by tuning the network properly, changing the hyperparameters, they were able to match the performance of the transformers. So if you want to use some architecture, today we use ResNet 18 and I showed you, but what are the other things that you can use? Don't be a hero. For most problems, you should use an off-the-shelf network. You don't have to design the network by yourself and train it and just waste computational power. If you are care about accuracy, you can use ResNet 50 or ResNet 101 or efficient nets B3 to B7 or ConNext. These are excellent choices. Efficient nets combine high accuracy with efficiency through compound scaling, and ConNext modernizes CNNet to rival transformers. If you want lightweight efficient networks, example of mobile and real applications, you can consider using mobile nets, ShuffleNet or efficient nets B0 to B2. That's a summary about the convolutional neural networks. Yeah. Any questions about that? Yeah.
So the current LLMs, are they models based on any of these models, or they're totally different developments?
They are based on transformers.
Or is it okay?
They are not convolutional neural networks. They are transformers. Transformers. Mm,
Different architectures, not
different
new.
architecture. Different architecture. Yes. This is the original picture of the transformer architecture. This is the original picture from Transformers paper. There's no use in looking at this. But you can see here they have so-called attention. Attention is the name of the game in Transformers. Multi-attention. They don't use convolutions. That's the thing about Transformers. So
Is it
transform.
correct to say for some clustering, it's better to use CNN, and for this kind of LLM kind of activity, we can use transformers? Would that be correct or not necessarily?
You would have been correct in 2021, but now for everything they use transformers. Even for images, they patch the image and consider these little patches as words, and they use the transformer. Yeah,
Even for image classification and
yeah,
things like
yeah,
that.
yeah, 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 yeah. Everything transformer. Everything transformer. So you can see I have not been able to achieve validation accuracy more than 75%, although the training accuracy is large, 86%. Why? Because we don't have sufficient number of training images. Yeah. So you can see the network is running now.
Does that mean like you were doing some training on that model? Would we, like, if we use a transformer model, would we do the same thing again? Just do the
Yeah,
training on
yeah,
that?
exactly the same thing.
Ah,
Training means fine tuning. Okay.
okay, right here
Training. If you when you say training, you think that you are
from
starting with the
scratch.
random weights from scratch. This is not something that we can do. Okay. This you can do, but this will be very expensive. You need the GPU machine, and when they train these models, they have thousands of GPUs working, thousands, billions of dollars invested for those. So we cannot do those. So, but we can do fine tuning. Fine tuning means slightly adjust the weights to match with our data set.
Okay, sir, got it.
Think about something like this now. You have a you use a large language model. Large language models are available now. So okay, so like for example, Quen 2.5 VVL or something like that. This model is available. This is from Alibaba. So see, this Hugging Face, it's available. So you can download that and get that running. Okay, it's not a problem. But one thing is, this has been trained on something. No? So if you assume that you want to get this model to mark assignments, your assignments, I have not done that. Then I have to train them on some assignments. So I need to have data for that. I usually use ground truth data also, assignment image and the assignment marks and some comments about the assignment. So I can get the model to do that for me. So you can see to adapt that to a different task, I will have my little bit of own data and then I fine tune the model. These are the things that you can do.
Okay, sir. I think I got it.
Actually, this
Thank
is
you.
what we want to show in that workshop. So if we can organize that workshop, I'll put a message in the thing. So
Thank you,
I
sir.
will we will do that hopefully. I'm not a person who's very good at doing these things, but I will. Students are there who are very capable of doing this. I will bring them and organize this. So validation accuracy actually reduced, turned out to be 50. I don't know why. So these kind of things happen. So that's using ResNet 18. We can use a bigger model also. Uh, Hopefully it will become better, and we can use some more epochs, and it will become better. So that is all I want to cover about convolutional neural networks. So then we can start the object detection part. Do you have any questions, more questions or discussions about the convolutional neural network?
So if we are going for a new project and we have a choice between CNN and this transformers, what would make us still use CNNs?
Yeah, that is a good question. I would use a CNN if the problem is simple, like a simple image classification, like classifying between these actors and actresses. I will use a CNN. But if I'm given a slightly difficult task where the I do not even know about the classes that can come, okay, I don't know, then I will use a transformers for that. Transformer based network. So VIT, SWIN, like that. So many things are there for different tasks. So if you go to now that all, yeah, that's a good question actually. You go to torch vision. So many models are there. Models and pre-trained weights. So if you go to models and pre-trained weights, this is the tutorial. So you see, okay, these are the classification models. That means you give a label to an image, cat, dog, or something. So these are the classification models they have. They have so many of them, right? So some of these words you heard today. So vision transform is also there. See, swing transform is also there. Yeah. Connext is also there. See, AlexNet is also there. These models you heard. Some of them you did not hear. Then the weights, different weights are there. See, and they have produced given you accuracies also. Different weights trained on ImageNet V1 and so on. and then quantized models. So they will reduce the size that is required by quantization. Those models are there. And then semantic segmentation, that means identifying, labeling each pixel. Semantic segmentation models are there. Object detection models are there. think, uh, then video classification models, key point detection models. So, and for different things, different models are there. Hugging Face also has those things. Hugging Face has transform models. So, Hugging Face. So, see, so many models, right? So, text generation models, image to text models, image to image models, text to speech models, text to video models. Models that many people trained. But one thing is you have to know about the model and who trained it and so on before you use it. So many of them, right? So many of them. So you have to, if you are in this field, you have to study. I also have not studied what is there, what should I use. So efficient net large model trained with this data set, I think. So like that, so many
Thank you,
models.
sir.
Yeah. So image to image, image to text, text generation, image to text. So writing something about the image. Yeah, so many models, so many of them. I mean, that's a good, it's a good question that you ask. So you have to know what model you want to use. Scout the models, read about them, and then text generation models. So DeepSeek models, DeepSeek very recent models. It's just updated 17 days ago, but parameter count is 158 billion parameters are there. From DeepSeek AI itself, DeepSeek people. Yeah. So this is a diffusion model, I think, for image generation from NVIDIA itself. For large companies. Yeah.
I think there is an additional thing which is going on now, this agentic AI, and also like they're building, so you can run an agent like kind of thing, which then again queries the main model which is running somewhere else.
True. Yeah.
The architecture is changing also now. I think they're just trying to make it more efficient because of the high bandwidth.
Yeah. When you have agents, multiple of these kind of models are running on some problem, and they can communicate with each other also, and to give a better solution. So if you want to pay some money, and you can add an extension. So you can see I have this agentic Claude, Claude Anthropic. So um, Claude and Codex. Codex is by OpenAI. So I think with this we can. I have not done that actually. With this, we can use agents. Yeah, but you have to pay money, I think, for this. Yeah. I have not done them myself. Yeah, but there are people who have done these things.
I
We
think
can actually organize a
recently
workshop. Huh?
I was looking at something here, and there was some kind of, I can't remember the name now. It's like a gateway. So once you install that, you can, for example, connect. You can like install. You can run a model locally, and then through that gateway, you can point to that specific one, and
Yeah, true. Very true. Yes, it is possible. Yes.
to save money, for the tokens. I tried that, but my machine is too slow, so I
Uh,
had to give. I installed, I think, LM Studio, and
uh,
then I try Nitro. I use Llama also,
uh,
Llama on the machine, and then I installed that interface, but it was a bit slow, so I gave up on that. And I think I use Quen for the model.
excellent. That's excellent. Yes. So I'm planning to organize a workshop. So hopefully, if that materializes, I will invite you all also, so that some experience in fine tuning these large language models and vision language models can be transferred.
Thank you, sir.
Yes. So thank you very much for those questions. So that actually concludes our CNN part. So under CNNs, we studied what CNNs are. These are convolution neural networks. So multiple convolutions run on the image. These are mainly for the images. So we mainly studied about, in detail, we studied about Jan LeCun's Lenet 5. If you remember, we computed the number of parameters that it has, and we hand coded that and implemented that in PyTorch, and we got that running for MNIST, and we got a very good accuracy for that. And today what we did was we studied some other networks, including ResNet, and today we downloaded the ResNet weights. The ResNet has been trained on ImageNet 1000 V1, and we downloaded those weights, and we were able to adapt that to classify the images of these four actors, including our own Honorable Ranjan Ramanayak also. And then we got some accuracy. So there are two things that people usually do about this. One is called transfer learning. That means you chop off the top layer and add a new top layer and train only that with a slightly high learning rate. And then the other one is called fine tuning. You let all the weights of the network be affected of the ResNet 18. That is usually called fine tuning. And we looked at existing architectures of convolutional neural networks, and ResNets are very good architectures. Efficient nets, B0 to B1 are small ones that can run on mobile devices and so on. And then there are large models B3 to B7 and ConNext. These are great models. And these models can be quantized also to make the memory footprint small. These reside in the GPU memory. So if you don't have a large GPU, that kind of quantization is very important. I think computationally also its advantages when you quantize. And then we looked at some models based on your questions available in Torch Vision and Hugging Face. And we briefly talked about the transformer. That's the part of the convolutional neural network. So now we can take a break and about 15 minutes, and then we can look at object detection afterwards. Mainly, I want to look at how object detection happens, and then use YOLO. I can explain you how YOLO works. Let's take a 15-minute break, and we can meet at meeting at 4:18, 4:35 or something. 35, yeah. 4:18, 35. Yeah, that's okay. That's reasonable. So I will stop the recording so that I can have two recordings for this.